Dr. K. Parinivelu, Professor at the Center for Environmental Studies and Director of Center for Climate Change and Disaster Management, Anna University, Chennai. He obtained his PhD degree from Indian Institute of Technology, Madras, Chennai. He worked as project officer for a brief period at IIT Madras and moved on to the Center for Environmental Studies, Anna University in 1992. He was a visiting professor at Chungam National University, South Korea during 2007. He has been teaching courses on environmental chemistry, environmental pollution control, and instrumental methods of analysis since last 27 years. He has guided 75 students for ME and MSc, 4 MPhil, 2 MS, and 15 PhDs. He has published 135 papers in journals and 90 in conference and symposiums. He has received several awards in national and international levels.
Welcome to the lecture series on environmental chemistry. We are discussing about soil chemistry. In the previous class, we discussed about soil formation and what are some important characteristics of the soil. In this lecture, we are going to discuss about what are the composition of the soil formed. This soil usually contains both minerals and organic components in it. In addition to this, the soil in the voids, they have water as well as air. That is also very important. We will see what are the mineral components actually in the present in the soil, and what are the major material of this, and as well as the organic components, what are the function of this one. If you look at the mineral components in soil, they are all classified as primary materials as well as secondary minerals, actually derived from the original rock material. The primary minerals, that is in the sand and silt, are the residues from the disintegration of parent rock material, and hence these are known as primary minerals, that is directly derived from the rock due to the disintegration, that is sand and silt fraction. These are all known as primary minerals. The other component actually present in soil is clay, and those in the clay fractions are products of chemical weathering and hence are often known as secondary minerals. That is due to chemical reaction from the original parent material, these clay things are derived, and because of this reason the clay is known as secondary minerals or clay mineral, and consists of mainly aluminum silicate and hydrated oxides of metal. The minerals in the clay fraction impact chemical and physical properties to the soil, which strongly influence its behavior. For example, in absorbing cations and anions, as well as even organic components like pesticide and acting as a source of plant nutrients also. So, both anion, cations, organic materials like pesticides as well as important plant nutrients, everything is binded to this clay minerals. Their properties can be best understood from a knowledge of their structure of this silicate minerals constituting the clay. The repeating units are linked to form sheets called tetrahedral and octahedral sheets of these mineral, which are all chemically combined. So, both tetrahedral and octahedral sheets are present in the clay minerals. Just look at this structure of this representation of clay mineral type, a kaolinite type of material. You can see here the silica is arranged in this tetrahedral form attached to 4, and if you look at the aluminum, these are all arranged or bundled together in a 6-way octahedral ring. These are arranged in a sheet type, and see the distance between these 2 silicate layer in between aluminum layer, that is tetrahedral, octahedral and 1 unit, and the distance is about 0.72 nanometer. That is a very small size of this octahedral layer and the tetrahedral silica layer. This is a top one tetrahedral fashion, and the middle one is a octahedral layer arranged. And also in these you can see a bonding, hydrogen bonding also possible between the OH and oxygen and hydroxide in the adjacent layer. There is a hydrogen bonding is also taking place. So, this all the hydrogen bonding, everything provides stability to this clay mineral. This is one example. The other minerals also arranged in this clay layers like this, either an octahedral and tetrahedral layers structure. And usually in this clay material, the aluminous silicate, the clay fraction range from crystalline through poorly crystalline to amorphous material. Certain clay minerals are available in the lustrous crystalline form, and certain materials are available in the amorphous form also. It varies. And all these clay mineral, whatever it is, consisting of repeating units of a silicon atom surrounded by oxygen atom in the form of tetrahedron, as I shown before, and an aluminum, magnesium or iron atom surrounded by oxygen atom and hydroxyl group in the form of octahedron again. These are all shown here. This is the aluminum bonded in the octahedral form, whereas in the silica it is in the tetrahedral form. It is bonded to the 4 oxygen atom, 1, 2, 3 and 4, whereas aluminum here it is 4, 5, 6. So, silica is a tetrahedral structure, and the other metal like aluminum or iron in the octahedral fashion it is arranged. And there are 3 type of layers in this among the clay mineral material, consisting of how these layers are arranged. For example, if it is 1:1 clay mineral, that is 1 tetrahedral, 1 octahedral sheet forms, then it is a 1:1 clay mineral, as in kaolinite shown above. And sometimes there is a possibility of 2:1 clay minerals also arranged, that is 2 tetrahedral and 1 octahedral sheet is arranged, that is another variety. For example, illite mineral and other thing, vermiculite, all this thing forms under this category of 2:1, that is 2 tetrahedral silica layer and 1 octahedral sheet of the metal ion. And 2:2 clay minerals also possible, that is 2 tetrahedral silica and 1 octahedral sheet plus an octahedral interlayer of magnesium hydroxide or aluminum hydroxide, as in the clay mineral chlorite. So, there are 3 ways depending on how this tetrahedral layer and octahedral layers are arranged. We have 3 type of clay mineral types. As before, as shown in the diagram earlier, the simplest is a clay structure of kaolinite was shown here with 1 tetrahedral sheet and 1 octahedral sheet of aluminum and 1 tetrahedral sheet of aluminum, forming a 1:1 clay mineral. Just we will go back and see the structure again. This is a arrangement, and successive 1:1 layers are stacked above each other and held together by hydrogen bond between the oxygen in one layer and a hydroxyl group in the next layer. This is also very, very important to provide stability for this clay mineral. The hydrogen bonds prevent the other groups from entering between the individual layer and keep the structure relatively rigid. Okay. So, the hydrogen bonds also play a very important role in this stability or rigidity of this clay minerals. And the tetrahedral sheet of silica, it may be replaced by aluminum, and in the octahedral sheet aluminum may be replaced by magnesium and iron ions. Okay. The cementite structure of monazite is electrically neutral, but substitution makes the structure electrically negative because of the substituting ions have a lower positive charge because of the change in valency number. Substitution of tetrahedral silica, that is 4, by a trivalent aluminum or a octahedral aluminum ion or by magnesium ion. Okay. You can see here silica by 1 lower oxidation state aluminum 3, the octahedral aluminum 3 by magnesium 2 if there is a replacement or substitution, that gives a single negative charge which is balanced by a cation held between silicate layers, okay, like potassium or sodium. The substitution is described as a isomorphous because of the substituting ion must be more or less should have similar ion size in which it replaces, like silica or aluminum, very close size. Similarly, aluminum and magnesium, if you see the size of this ions they will have, that is very, very important. Then only These type of substitution, normally known as isomorphous, may take place in this clay mineral. And clay actually binds cations such as calcium, magnesium, divalent, monovalent ions like potassium, sodium, ammonium, all these things possible, which protects the cation from leaching by water, but keeps them available in soil as a plant nutrients. If there is a need, definitely these ions can be leached out. Otherwise, because of the electric force here, they will be held strongly attached to the clay minerals. Whenever there is a need, they can give out to the plant material as a nutrients. So, apart from the major thing clay we have discussed, the inorganic components of soil, mainly if you look at it, that is actually present in the earth crust, oxygen and silica. That is, silica is a main material, SiO2, okay, mainly consisting of oxygen and silica. The other ions are aluminum, iron, calcium, sodium, potassium and magnesium are present in the other decreasing order. Therefore, mineral composed of these elements, particularly silicon and oxygen as a silicate mineral, constitute most of the mineral fraction of the soil. These are the roughly 75% we can say consisting of silica. So, common soil mineral constituents are finely divided quartz, that is a silica, orthoclase, potassium aluminum silicate, zeolite, that is a iron oxide, magnetite, again ferric oxide. So, these are the major fraction through which consisting of inorganic components of the soil. Coming to organic fraction of the soil, which consisting mainly humus materials are present in the soil. So, an organic component is an essential ingredient of any healthy soil. As I mentioned before, 5% should constitute the organic part. Okay. So, that is what healthy soil in which we can expect a normal agricultural production. And the organic substances consisting of humic, fulvic acid, humus material, all those things, and contain exchangeable sites because of the presence of carboxylic acid as well as OH group present in this humic acid and fulvic acid. They provides cation exchange property, carboxylic acid, in which the H plus can be replaced with other cations like sodium, potassium, calcium, magnesium, etc. And if you see the major classes of organic components actually present in the soil: humus material, fats, resins and waxes, saccharide, carbohydrate material, and nitrogen containing organic components, as well as phosphorus containing organic components also constitute the organic type. And if you see the properties of this humus material, it is actually the degradation of residue from plant materials. Originally vegetation materials, plant leaves and wood, everything undergoes degradation, the decay leads to this fractions, humus material. What is the significance of this humus in soil? This is actually most abundant organic component and improve the soil physical property, exchange nutrients, as well as act as a reservoir of fixed nitrogen. Okay. So, these are the some of this special about humus material actually present in the soil, which is actually derived from vegetation. The next type is a kind of fat, resins and waxes. All these things constitute as a lipid material, that is hydrophobic in nature and extractable by organic solvents, okay, not soluble in water usually, only it is these fraction or composition can be extracted into organic solvent. And generally only several percent of soil organic matter may adversely affect soil physical properties by repelling water and perhaps sometimes phytotoxicity to the soil, okay, natural toxicity by this fat material, but one of the properties is water repelling, because of these materials are lipid soluble and provides water repelling property to the soil. Saccharides consisting of cellulose, starch, hemicellulose and gums, all this one, and these saccharide materials serves as a major food material for soil microorganism actually living in the soil. Okay. So, these saccharide materials are very easily degraded into food materials for this microorganism actually present in the soil. Not only this, these saccharides helps to stabilize soil aggregate formation also, acts as a binding agent, these saccharide materials, and helps in formation of larger aggregates to the soil. So, in that way the saccharide materials composition also very important to the soil. And then next, nitrogen containing organic materials, that is nitrogen bound to humus material, amino acids and amino sugar and other things are part of this nitrogen containing one. And these nitrogen containing material provides nitrogen for soil fertility, and that is again very important, that comes through the nitrogen containing organic material in the form of amino acids or nitrogen containing sugars. Other aspect is phosphorus, because along with the nitrogen, phosphorus, they will always goes together, that is very important for the production of agricultural crops. So, phosphorus compounds present in soil organics also very important, and these phosphorus compounds usually present as a phosphate esters and phosphate like phytic acid and phospholipids, these materials also present, and again these are all source of plant phosphate, which is again one of the important nutrient along with the nitrogen. So, in this way the major organic components actually present in the soil are grouped, their significance, how it is very important for a healthy soil is highlighted in this slide. The solid fraction of organic typical for a protected soil what is approximately 5% of organic matter, that is very important, and rest we see 95% of inorganic matter things apart from soil, water and air. Some soil such as peat soil may contain as much as 95% organic material sometimes, and at the same time there are possibilities certain soils may contain as little as 1% of organic matter. Okay. And roughly about 35% of the volume of the typical soil is composed of air filled pores also, through which a lot of microorganisms including earthworms moves around, that makes it a healthy soil. So, roughly about 5% of organic matter is very much essential for agricultural production. So, various ions are present in this soil, and soils also have very key chemical characteristics because of this ion content present in the soil. And the surface of certain soil particles, particularly the clay, hold groupings of atoms known as ions. So, I told you because of the negatively charged clay particle, aluminum silicate, most of the cations are attached to this by electrostatic attraction, and these clay materials carry a negative charge because of the silicate one. Like magnets, these electrostatic forces, that is these negative ions called anions attract positive ions and electrical neutrality maintained, and through this negative ions very important ions like potassium ions are attached to this soil, and cations including especially those from calcium, magnesium, potassium especially, then becoming attached to the soil particle in a process known as cation exchange, that we will discuss elaborately in the next lecture. The chemical reactions in cation exchange make it possible for calcium and other elements to be exchanged into water soluble forms that plants can use as for food material. Therefore, the soil cation exchange capacity is one of the important measure of its fertility. So, if a cation exchange capacity is more, definitely that soil is considered to be very fertile, that reflected by this ions or cation exchange capacity actually present in the soil. Charge on the soil is another important, that also provides whatever the cation exchange capacity I mentioned, that is important. So, soil contains clay mineral and organic matter. as a result of weathering and the addition of organic debris, usually the vegetation material. Soil acts as a buffer zone between atmosphere and groundwater and provides plants a steady state of supply of nutrients through this clay minerals and organic matters present in it. And soil have this softy property because of the electrical charges and large surface area of clay minerals and humus actually present in the soil. So, the clay mineral and humus material originally present in the soil provides this charge. Because of their structure and chemical composition, the clay mineral as well as humus material which contain carboxylic acid and OH group usually bears a negative charge. The charge is pH actually dependent from the surface of the clay mineral, that is aluminum silicate and hydroxide oxides of iron and aluminum, and from acidic groups actually present in humus, and protons dissociate and provide negative charge. This dissociation of protons gives a negative charge which is again pH dependent whether it is acid medium or alkaline medium. Hydrous oxides of iron and aluminum present in clay mineral becomes positively charged at low pH. Iron and aluminum or manganese, they at low pH condition, acidic condition, acquire a positive charge by adsorption of protons that actually comes from acidic condition or low pH value. And electrical charge on clay and humus also important, that is the permanent negative charge on 2:1 and 2:2 clay type of mineral due to isomorphous substitution because of the replacement of higher valency ions originally present by low valent ion substitution. Already I mentioned this is way it may provide electrical charge, and pH dependent charges as is shown here, that is negative charge at broken surface and edges of clay mineral. The silica hydroxide and aluminum hydroxide originally present at alkaline condition. What happens is the OH medium pick up protons, makes it dissociate and converts it into negatively charged ions here. As the negative charge is shown here, the OH is converted into water molecule, and suppose the reverse condition is possible. At acidic condition, what happens is the positive ions will be absorbed by this aluminum ion, and this one becomes negative positively charged one. So, it depends on pH of the surrounding medium, the water solution pH, what is it actually. And the negative charge also comes from the humus material. COH and OH group, phenolic groups are part of this humus material. Again depends on the OH or proton, acidic or alkaline, and in alkaline condition what happens is this OH will pick up proton and converts into negatively charged ions. Same thing with OH, phenolic group present in the humus material. To alkaline condition, it removes the proton and makes it negatively charged ions, and negative and positive groups of a hydrated ion are also shown here, that is the iron oxide hydroxide at alkaline condition again remove this proton and makes it negatively charged ions, whereas the same thing at acidic condition picks up protons and becomes a positively charged ferrihydroxide ions. So, depending on the surrounding medium, this soil will acquire positive or negative charge. So, depending all this thing, the soil water, we call it as a soil solution, from which all the nutrients everything present, through that only the plant material takes up or utilizes the soil solution, which is very very important. So, the aqueous portion of the soil that contain dissolved matter from soil, that is chemical and biochemical process happening in soil, provides or dissolve all this ion and take it to this aqueous portion of the soil, which is normally known as soil solution. And this also provides intimate contact between the solute and soil particles. Okay. The aqueous solution is an intimate contact with the solute actually present and the soil particles. This actually makes it, and there is a possibility dissolve and take it to this whatever ions that will come up with it. and this soil solution actually provides water for plant growth and act as a pathways for the exchange of plant nutrients between the plant root and solid soil. Okay. So, in that way soil solution is very important, and this soil solution actually contains all the essential nutrients, potassium, calcium, all these ions, because of the water solubilization and exchange reactions comes part of this soil solution, and through which the plant materials actually supported in the soil takes up essential nutrients that is available in the soil solution and makes it a ideal growth. That is, the dissolved mineral matter in soil is largely present as ions. The soil solution, whatever it is, as a soluble ions it is present, that is prominent among the cations are responsible for this acidity, calcium, magnesium, potassium, sodium ions, and other ions which is usually available at a very low concentration or trace concentration are ferrous, manganese 2 and aluminum 3 ions. So, these ions like potassium, calcium are very much essential for the plant growth, that is also part of this soil solution, and they are also attached to this solid soil particle whenever necessary, and these are all made available to the plant material through soil solution to the root, through which normal plant growth will take place. So, in this way the soil solution, it is in contact with the soil, actually both mineral as well as organic matters are present, and that contribute to the soil solution contribution. So, with this we have come to the end of this composition of the soil. We have made a look at what are the composition, and healthy soil contains equal amounts of air and water, and 5% of organic matter and about 45% of the mineral content should be present, that is inorganic thing should be, that is normally considered as a healthy soil. And if we look at the mineral composition, clay, which is very important because of the negative charge and cation subsequent cation exchange capacity, along with the organic humus minerals, they all possess negative charge, ultimately bind very important cations which is required for the uptake for the plant growth. So, this way the mineral components consisting of inorganic clay and silicate as well as organic matter consisting of mainly humus and nitrogen and organic containing organic compounds also very much essential for the growth of plant materials. Thank you.